Okay, in this video I'm going to talk about the reflections of the foot of an altitude of a triangle with respect to the sides. So let's say that we have an arbitrary triangle. We consider an altitude in this triangle, and this is the foot of the altitude, and we consider the reflections of this point with respect to the other two sides. So like this and like this. So this point and this point. So reflections means that these angles are right angles, and these segments are equal and these segments are equal. So, and the main theorem is that these 2 points lie on the same line as the line connecting the other 2 feet of the altitudes in the triangle. So we have the other 2 altitudes and this feet of the triangle, so this line. So these 2 points, the reflections, it turns out that they lie on this same line. Yeah, so let's denote the points B, C, H, B, H, A, H, C. So let's denote this point by P, Q. And so now the theorem says that HA, H, C, P and Q, these 4 points are collinear. Okay, so let's prove this. So I will prove that one of these points lie on the, let's say Q lie on the line HA, HC, and the proof for P would be similar, so there is no need to consider them like both of them separately. So let's draw the triangle again, and we consider now only the point Q here. Now instead of the point Q, actually we are going to consider, so this is the point Q, right? So but instead of this point Q, we are going to consider the intersection point. So let's draw everything. B, C, H, B, H, A, H, C, and so now we draw the line H, C, H, A, and instead of considering the point Q, so we don't yet know if Q lies on this line, but we consider the intersection point of this line HC with this line, so with the line HB, like this point. Let's denote something K. So HBK, and we denote this point by Q prime. So Q prime by definition is we define it as the intersection point of HA, HC and HBK. Right? So, and we will prove that it coincides with the point Q, and to prove that, it is enough to prove that so it is enough to prove that Q prime K is equal to KHB, right? So if we prove that Q prime K is equal to KHB, then it would mean that Q prime is exactly the reflection of HB with respect to the site AB, right? And if it is a reflection, then it is the same as the point Q. So okay. So it is enough to prove that, to establish, to prove that Q is equal to Q prime. And then this in turn would imply that Q belongs to this line. So, okay, so so now we notice that, so we connect like this, and we notice that this angle is equal to this angle. So this is because the quadrilateral, this quadrilateral that I highlight in blue is inscribed or cyclic. This is because it has the angles. So the angle, this angle, is equal to this angle and is equal to 90 degrees. So the angle AHCC is equal to 90 degrees is equal to the angle AHAC. So because of the equality of these two angles, it implies that this quadrilateral AHCHAC is cyclic. It's one of the criterion of cyclic quadrilaterals, and because it is cyclic, we immediately conclude that the angle BHCHA is equal to the angle C in the triangle. So this angle is equal to this angle, and this is another criterion of cyclic quadrilateral. So the internal angle at one vertex is equal to the external angle at the opposite vertex. So now similarly, if we consider this quadrilateral, it's also cyclic for the same reason, basically. We have two right angles, right? So the angle, in this case, BHCC is equal to BHBC, right? So BHCC is equal to 90 degrees and is equal to BHBC. From this, it implies that this quadrilateral HCBCHB is cyclic, and this implies that the angle, this angle, external angle at one vertex is equal to the internal angle at the opposite vertex. So the angle AHCHB is equal to the angle C in the triangle. So now we see that, like in these two equalities, the angle C is the same on the right hand side, therefore these two angles are equal to each other. So from this it follows that the angle BHCHA is equal to the angle AHCHB. So on the picture it's these two angles, this angle and this angle. Right now one of them is also equal to this angle, right? It's just the angle between the two lines. So let's write this. So BHCHA, so this angle is equal to the angle Q prime HCK. Right, so therefore these two angles are equal to each other, and from this it follows that well, it means that, so again on the picture, so these two angles are equal to each other. This simply means that HCK is a bisector of this angle, right? So HCK is a bisector of the angle Q prime HC HB. Now like if we consider the triangle like this triangle that I highlighted with yellow, Q prime HCHB. So in this triangle HCK is both a bisector, as we just established, and it is also an altitude, because this angle is a right angle, right? So in the triangle Q prime HCHB, in this triangle HCK is a bisector and an altitude. Because it's both a bisector and an altitude, it immediately follows that this triangle is isosceles and that this segment is also a median. So from this it follows that the triangle is isosceles, which means that Q prime HC is equal to HC HB, and that this segment HCK is also a median. So HCK is a median, which means that these two segments are equal to each other. So Q prime K is equal to KHB, median, which means that Q prime K is equal to K HC. Now this is actually what we needed to prove. So we recall here. KHB, no, I wrote HC, no, not HC, but HB. Of course, HB. Again, so Q prime K is equal to KHB. So these two segments are equal to each other. So yeah, so these two segments are equal to each other. So as already mentioned, this implies that this implies that Q prime is the reflection of HB with respect to the side AB. So this means that Q prime coincides with the original point Q. And so now because Q prime by construction lies on the line HAHC, and Q prime is really the same point, it means that Q lies on this line. So it follows that Q belongs on the line HAHC. And that is basically what we needed to prove. So now similarly, the point P also lies on this line, HAHC. And now this means that all these 4 points, HAHC, P and Q, all 4 of them are collinear. Yeah, and this concludes the proof.